stars. Okay. Here's time to start the stream. Yes. In theory, the stream
We are
has
live.
begun. We're live, yeah. And now, of course, as usual, we require someone to let us know that we exist. Oh, there we go. Someone says
Validate
that we
our
exist.
existence.
Yeah, exactly. It's the standard joke, right? No one watches the show, did the show ever happen? Right on time. Of course, we're right on time. Crush not. Morgan really whipped me into shape. I had this rough idea about time, when things should start, and Morgan really brought in that sense of obligation to the fans.
Yeah, if I don't have a schedule, then my life falls apart.
Yeah, is that true? Like, are you on time all the time?
I would like to think I'm on time all the time. It's not true that I have an ironclad schedule, but if I have an appointment or a meeting or something, then I feel terrible if I'm like even a minute late.
Yeah.
So I'm more likely to get there like 10 minutes early than to be a minute late.
Yeah, I'm pretty similar. So anyway, hey everyone, welcome to Open Space. This is of course a live QA with me and some of my space friends. It's like we should have like.
Glad I could be like the very last of our colleagues to the show. And you're really scraping the bottom of the barrel at this point.
Oh, no way! Are you kidding? It's you before. Man, who have we got next time? Well, I'm gone for 2 weeks with Paul in Costa Rica, and we'll probably record some episodes while we're there. And then we've got Jesse Christensen from Tess and Kepler, and then I forget a bunch of other guests. So I'll
wonder
put them
when
in
the
schedule.
Test floodgates are going to open.
They're
Because,
starting
right now we've
already.
had like 1 or 2 or 3, but at some point they're just going to dump like 1,000 on us.
Yeah. Oh,
and it's going to be like the Kepler days all over again.
And before I go any further, just to let everyone know, tomorrow, and I'll put the event in a moment. Tomorrow, at a very special time at 4:00, I've got a very special open space. In that my guest was very cool, but he wasn't able to make any other time, and so it's Phil Torres, who is an expert on existential risk, and we're going to be talking about the end of everything. So that'll be tomorrow at 4 p.m. So just
man, that's got to be a bummer of a job.
I know.
It's like how do you leave that at the office when you come home at night and it's like, oh yeah, I spent all day thinking about how the world is definitely going to end.
Yeah.
But now I'm going to cook dinner. And...
Yeah. What do you want for dinner, hon? Who cares? It doesn't matter. The robots will destroy us all. All right. So anyway, who are you and what do you do?
Well, I am Dr. Morgan Rehnberg, and I am an astronomer, a science communicator, a general talking head, a doer of things, and a consumer of stuff. My day job is as the director of scientific presentation at the Fort Worth Museum of Science and History, but I also write and podcast and read and do things, and generally be amazed at what's out there in the world, because it's a pretty darn cool place.
Yeah. So how did we meet?
We met back in 2013, maybe. So when I entered graduate school in 2012, I sort of committed myself to not getting sort of pigeonholed down into the tiniest possible little narrow field of science, which is what happens to most graduate students. And my solution to that problem was to start a blog and a podcast to talk about the news in astronomy in fields other than what I was working in, which was the rings of Saturn. And so I started my blog, and a few months later, I started contributing a podcast to the 365 Days of Astronomy podcast with CosmoQuest. And I did a year or something of that. And then when it came up time for me to renew for another season, I told them that I would, but only if I got to be a guest on the Weekly Space Hangout, because I thought, hey, that seemed like a cool, it was very different back then than it is now. And
now
so
that
would
you're
have
in
been
charge.
First time we met. And my first episode remains one of the most memorable ones that I ever had, because I came on, I think, planning to talk about some sort of funding situation with the Mars exploration program, and they must have been renewing funding for Opportunity or something like that. And one of our guests was, of course, Casey Dreyer from Whiz of Space Numbers from
Right.
the Planetary Society. And not like 1 minute after the show had ended and I had given my first segment, I had this like 5-paragraph email from Casey Dreyer describing how I should talk about the priorities of planetary science and astronomy for a public audience. In case he was incredibly nice about it,
Yeah.
but it was just, I was just blindsided by
Oh.
somebody who had obviously thought about this for many years, and it made me wonder if it was even worth trying to do that sort of thing. But I came back the next week, and most weeks in the 5 or 6 years since then.
Yeah, yeah. I mean, if people go back when it was a round table of different co-hosts, often Morgan would be there, and then there were many cases where it was just me and Morgan.
Those are always the most fun because you can dig the deepest into. And we do a better job of that on the Weekly Space Hangout now. Back then, you got your 3-minute speaking slot, and then there were 8 other people waiting to say their thing too.
Yeah.
And so you could never get that deep into it. But I think we've struck a better balance now with fewer stories and more time to enjoy them than what we were doing back then.
And the thing that I like is that you are the planetary science expert. It's great now, right? We have a astrophysicist with Paul. We have a planetary, or we have an exoplanetary astronomer with Kimberly, and then we have a planetary scientist with you, and then we have a janitor with me. So
you keep us all focused on actual things.
A ring leader, I'm not sure, but so for people who maybe don't know that part about your history, like where did you go to school and get your PhD?
Yeah, so I went to the University of Colorado in Boulder, where I was just back this weekend, and I worked at the Laboratory for Atmospheric and Space Physics, which is one of the nation's great planetary science organizations, and it has a history that dates back all the way to the 1940s when they were doing the first rocket testing with captured German rockets after World War II. And I spent my career working on the Cassini mission to Saturn, which I actually got started on years before I even went to graduate school. As an undergrad, I worked on a different part of the Cassini mission. And then I made this sort of pathetic attempt to escape Cassini in the latter part of my undergraduate time, and then got dragged back into graduate school. And what an amazing experience it was to get to work on such an exceptional and large and international mission in a way that even today very few of the big science missions are nearly as multilingual and multi-locational as Cassini was.
And what was your doctoral thesis on?
Yeah, I used a particular instrument on Cassini called the ultraviolet imaging spectrograph, which is basically a camera that took images in the ultraviolet and then made a spectrum out of each pixel, so you could see it in different wavelengths of infrared and visible light. But there was actually a special part of that instrument called the high-speed photometer, which was really just a super precise, super accurate light meter. And we could make measurements of star brightness up to 1,000 times a second for a single star in the sky. And so what we would do is we would point the high-speed photometer at one of those stars. We'd watch it pass behind the rings. And you can imagine the more stuff between Cassini and that star, the dimmer the star would appear. And we made the pretty reasonable assumption that that stuff was primarily in Saturn's rings. And it let us turn this measurement of star brightness into an estimate of the density of the rings for just a tiny infinitesimal slice across the rings. And what was so valuable about that is because we could make these measurements up to 1,000 times a second, we could make observations of the rings that were 10, 100, or even 1,000 times higher resolution than we could get with cameras. So the cameras on Cassini usually were capturing images that were something like a kilometer per pixel, which I always thought of as sort of studying the rings at the city block scale. And then with these stellar occultations, as they were called, we were often studying the rings in the scale of a few meters from 1,000,000 kilometers away. And that let me do work studying the rings basically on the smallest scale, for the smallest scale structure that anybody had ever looked. And we found millions of little tiny holes and gaps in the rings that revealed that their structure is not the sort of simple, smooth, continuous thing that we see when we see a picture, but it's actually more like a crocheted Afghan, where you have these sort of strings of stuff and then a whole lot of empty space in between. And it's just that we're so far away when we take a picture that we don't see those holes. We just see it all kind of averaging out to the color and the texture that we see in the rings.
Wow. And so then, you defended your doctoral thesis, which I'm sure was difficult and not a lot of fun. But then instead
it's not as bad as people make it think. Everybody makes it sound like a horrible thing. And once you spend a bunch of years working on something, I think it's kind of fun to get a chance to get up and talk about it in front of a bunch of people who are interested.
Well, my hope is that the work that you already had as a science communicator had made it easier. Like, did it make it easier for you to defend your thesis, or was it worthless?
Oh no, I think it was very useful, because when you do a PhD defense, you're speaking to your advisor, who has been intimately involved in your work from day one, but then everybody else in the audience, from the other people on your evaluation committee to just sort of random folks who wandered in the room, are scientists and maybe even astronomers, but they're by no means specialists in what you're doing. I wasn't talking to a single other person who worked on Cassini or who had ever studied Saturn. And so a lot of the techniques that you use to talk to intelligent audiences, which is what we do every time we do science communication, are just as useful when you're talking to an intelligent audience that knows some of the same things that you do, but has really no idea about the details of what you were working on.
And I mean, had you always been fascinated in Saturn and navigated your way to that program at Boulder, or would you have been happy to work on any mission, anything, as long as it sort of moved you into that field of planetary science?
Yeah, I had really no particular affinity for Saturn. And in fact, going back a little bit further, I had no particular affinity for astronomy in general. I knew probably for a good chunk of my life that I wanted to be a scientist, but I really probably couldn't have said a lot about what kind of scientist I wanted to be. In fact, when I graduated from high school, I was really intending to go into chemistry. And I was thinking I might be like a high school chemistry teacher. And my father sort of talked me out of being a high school chemistry teacher by saying, man, you don't want to deal with a bunch of kids like throwing acid in each other's eyes and things with that. And so he talked me into doing physics instead of chemistry, because, dropping things and rolling cars and stuff just seemed like a lot more fun than having to keep a bunch of children alive while also trying to do science. And so I went to college intending to be a physics teacher. And so I became a physicist. It just happened that my advisor that I was randomly assigned in college was an astronomer. And she was doing work on the rings of Saturn and invited me to participate in the work that she was doing. And that sort of started me off on this path that culminated with where I am today. But had you interviewed me as a freshman or a sophomore in college, astronomy probably would not have been a word that even came out of my mouth, because I was as interested as anybody else probably watching this show was, but I didn't have any special passion or desire for it. It was just a cool puzzle to solve among a whole load of cool puzzles that make up science.
And so last week we talked to Kimberly and sort of this journey again through the science, but also this realization that she didn't want to be a researching astronomer, and shifted her focus into journalism, like explaining the work that's being done, and is really enjoying herself. So did you, like, why did you have that same kind of realization? You guys must have talked about this, but did you? What was the journey for you?
I don't know if there was never like an aha moment, and the fact that I started a blog and a podcast like before I even started graduate school is an indication that it was something I must have been interested in really before I had any real experience with being a research scientist. And generally, my whole life has sort of just been being amazed at things and just loving the incredible variety and intricacy of what's out there in the world, and so I think that lends some interest to wanting to not just be stuck thinking about one thing for the next 30 years, but to really have an opportunity to think about a variety of things. And as an astronomer, that was thinking about all the fields of astronomy. But as I sort of went along, that feeling was stronger and stronger, and that led me to think about not doing what Kimberly did and going off to be a planetary science journalist, but to look even broader. And that kind of directed me in the direction of the museum world, where now I get to think about not just physics or astronomy, but math and computer science and biology and chemistry and history and all of this stuff that weaves together to make the world we see today. And I basically get to do the 10% most interesting stuff from all of those areas, rather than the 10% most interesting and then the 10% next interesting, all the way down to the most boring stuff in astronomy. And maybe that's like taking the easy way out, but it's a very satisfying experience.
I know exactly what you're talking about, and I think that's the same thing for me, which is like I'm very much like, once I've had a chance to like figure something out or see it and like, oh, that's so cool, I'm bored, and then I just kind of move on. And so I've got a career that allows me to just nonstop look at interesting things every day for the first time, and then be as curious about them as I need to be or want to be, and then I get to move on. Today I'm working on a video script about landing heavy payloads on Mars and how difficult and complicated it is. And it's really interesting, but I don't think I would want to think about it anymore. I'm like, I'm done.
No, I think about it a lot when I'm script writing, that like the first 300 to 500 words is just like so easy because it's just all this really cool stuff. And then like every 500 words after that is 3 times harder.
Yeah.
And so when you get to the point of like having to write a book or something, now you're slogging through all of the minutia of the thing that is what makes it up, but is not what really makes it amazing. And so it's nice to be able to skim along the surface and just kind of drift among the fun parts of the universe.
So people are starting to throw some questions into the chat, and I think that's kind of the fun part next, is for us to dig into some of your questions, both about, again, Morgan, you may not realize just how many of the SciShow Space episodes Morgan has written, but go ahead and pause any of them near the end.
Probably written somewhere between a third and a quarter of the ones for the last couple of years, and now I'm starting to write some scripts for the main channel as well. And that's been they're just amazing people, and they're a top-notch organization that you're lucky as a freelancer when you find somebody who will like treat you right and pay you on time and allow you to offer input. And I couldn't be happier with them as coworkers, and so it's fun to just get. And I have always been really excited about stuff in the world, but I'm not sure I've always been the person that like has a lot of great original ideas like that. And so when they hired me, I told them that I would write anything that they wanted me to, as long as I didn't have to pitch them. And it's worked out great, because I've uncovered so many stories that I didn't even know were things, like in astronomy, things that I just had no clue were things. They say, can you write 1,000 words about this? And I was like, I had no idea that there was like a giant pulse of gas moving through the Milky Way. But it's cool, and I'm glad that I got exposed to it by sort of being forced into it.
And that's my job. Like with our team at Universe Today, my job is to hand out those assignments. And so
Yeah, I don't want that job.
I love it. I love it. That's like my favorite part. The having to write it part. That's the part that I love to hand off to the writing team. All right, so I got a couple of good questions here. This one, Kayla Thompson. Congratulations, Kayla. Everyone's congratulating you in the chat. So Kayla wants to know, what's the probability of finding life versus the probability of finding intelligent life? So what do you think? Life versus intelligent life out there in the universe.
Yeah, I mean, all we can do is draw and extrapolate from what we know. And what we see on Earth is that there are millions of species of less intelligent life and one or two or three species of intelligent life, depending on kind of how you want to draw your boundaries. And so that might be an indication of the prevalence of those things in the universe, but that's not the same thing as finding it. One imagines that it is much, much easier to find intelligent life than non-intelligent life, because they're doing all the same things sort of dumb life is doing, plus they're polluting a lot in their atmosphere, plus they're trying to communicate, plus they're perhaps building Dyson spheres and all of that sort of thing. And so it seems like even if there might be 1 in a million species that are intelligent, the odds of finding an intelligent species just sort of in a gut sense feel a lot higher than that. Like, I don't know, 1 in 1,000 or 1 in something like that, 1 in 10,000. Yeah.
Now, I don't know if you heard, Kimberly and I had a bet last week on whether...
I remember taking Kimberly's side, but I don't remember what the bet was.
Right, so it was whether we find evidence of life here in the solar system first, or whether we find it with telescopes around, in the atmospheres of other star systems.
Yeah, and I think it depends on what you call evidence. I think this is the sort of profound problem with searching for life in the universe. And I've just done some writing about this, and sort of top of mind, is that there are myriad ways to imagine finding indications of life. There are basically one way to imagine finding proof of life, and that's to get a SETI signal that just says hello. Everything else just seems totally, we'll never know enough and be certain enough to really know.
Yeah.
Unlike with planetary life in the solar system, you could imagine eventually Mars 2020 picks up a rock and the next mission brings it back to Earth. And we see those things wriggling around in the Mars rock or something, and they don't have DNA or anything. It feels to me there's a much higher chance of finding provable life in the solar system, even if the odds of finding an indication of life might be higher outside the solar system.
People always ask me this question. They say, how do you think we'll handle finding life on Mars or finding life in space? And my guess is they will argue about it. It'll never be decided, and then they'll forget about it. That's how people will feel. And the reality is, we've already found life twice on Mars, right?
Yeah,
the Viking mission found life in an experiment that they did where they had some Martian regolith, and they added a bunch of chemicals to it, and it gave off some waste gases that said, oh, there could be life here. And people argue about it to this day. And then, of course, there was the announcement that Clinton made back in the 1990s, where we found life on Mars, and they found these little wormy creatures in this
ALH doubles 84
ALH, right. And astronomers argue about it to this day. And so
there's only 2 ways to know. One is to get an absolutely unambiguous signal from outer space, and the threshold for that would just be enormous. And the other is to bring back a sample from somewhere in the solar system and have that life be so different from life on Earth that it's just unambiguous. Because you can imagine life that looks different than anything we've ever seen, but isn't so different that we can't prove that it's not contamination. But if you find something without DNA, with some totally other internal structure, that seems as good as evidence as you're going to get.
Yeah. So I just think we'll be bored. We'll argue, and then we'll be bored and we'll forget about it until someone reminds us and does a video on YouTube about it, and then some people will notice that. All right, Crushnut asks, as science communicators, do you ever get bogged down in pedantic debates with yourselves and colleagues over how to explain science stuff to your audiences? We don't argue. We don't get into pedantic debates, do we?
Not with each other. I think that there's some more friction between sort of like research scientists and communicating scientists, because a lot of my philosophy has always been that I'm less interested in being sort of right than sort of leading you to the right idea, and that's, as scientists, we're really trained not to like that. The idea of not being exactly right and allowing sort of misinformation is just like abhorrent, and anathema to the scientifically trained person. But those details are almost always just like pointless and meaningless, and necessary so that we know and understand the world, but not necessary to understand like why we should care. And so I think there's a lot of sort of distrust between in both directions, between the people talking about science and the people doing the research about how we frame and talk about, especially like a subset of things that are particularly difficult to talk about.
Yeah, and I can remember sort of one wave of it that was back in the early 2000s. Think about like the work that, say, Brian Greene was doing with the Elegant Universe and his work on string theory and other string theorists, where it's the promise of string theory is that it is the universal theory of everything. It explains how gravity and electromagnetism come together and become one force, and everything else you want is all explained in string theory. And Brian Greene is really good at explaining it and turning things into analogies and going on shows and writing books and then more recently, and back in the day, right, there was of course Carl Sagan and the work that he did with Cosmos. He got a lot of heat.
Oh yeah,
and then,
he was not a popular person in the scientific community for quite a long time.
And most recently, we see, for example, Avi Loeb talking about Oumuamua and what potentially it could be, whether it could be a solar sail or some von Neumann probe or something like that. And so you've got this challenge. And just to reference another episode that we had of Open Space, Jason Wright was like, why are we allowed to talk about dumb life, but we're not allowed to talk about smart life, right? What's so bad? Like, let's just talk about it all. So it's, and those are the kinds of things that the public wants to hear. Like, they want to know this stuff. And we as science communicators have to walk that fine line between giving the fans what they want, but also making sure that we are scientifically accurate and being responsible for the work that we do.
The funny thing is that line cuts both ways. Because, for example, I think we all have given Avi Loeb a lot of crap for sort of floating what is technically a possibility, that, Oumuamua is an alien spaceship, but saying it's not worth having that. On like the flip side, you get scientists who always want to hedge their bets about things, and sort of the classic example of this is like climate change, where scientists want to say like the preponderance of our evidence suggests that humans are the cause of global warming, or that this has been the warmest year on records, or warmest year since 1881 or something. And it leaves open this sort of door of doubt that they don't intend to communicate, but as scientists, we're just always trained that you basically can never know anything for sure, and that causes problems, profound problems for public trust in science, when it feels like astronomers or scientists in general are never willing to take a stand, when really they're just sort of letting their proper professional judgment sort of escape its bounds a little bit more than is desirable.
Yeah, but then you also see these examples where people are like, before you told me that eating fat was bad, and now eating fat is good, but now eating sugar is bad, but now eating sugar is good. Like, make up your mind, scientists. And the problem, of course, is that science just as we gain more evidence, more knowledge is gained. Like it's just, and it can flip
Yeah, well,
back
and
and
the
forth.
physical sciences and the life sciences approach certainty in profoundly different ways. And it is exceedingly rare to see those kinds of flip-floppy statements coming out of the physical sciences because we generally would wait until there's only like a 1 in a million or a 1 in a billion chance. And as we were talking about before the show, with something sometimes like with the bicep results, that's not enough.
Yeah.
But in the social sciences, for very good reasons, we'll often talk about things that are much more likely to be wrong because we're never going to be able to survey a billion people or take the temperature of 10 million people to get to that level of significance that physical scientists enjoy. If we ever want any results from life sciences, the things that cure cancer and improve our nutrition, then we have to accept that increased chance of being wrong. But then we also have to kind of discount at least a little bit the flip-floppiness that it seems like is happening. We can't have it both ways.
Curious Borg asks, why is Saturn so light and fluffy? It's almost as big as Jupiter, but a tiny fraction of the mass. You could float Saturn.
You could. The funny thing, it's like a funny quirk of physics. So it turns out that when you have a gas giant, adding more mass actually makes the planet smaller. And so if you had a planet twice the mass of Jupiter, it would actually be smaller than Jupiter is. And that's because basically the extra mass being added increases the power of gravity faster than that mass takes up additional space in the planet. And so if you kept adding mass to Saturn, eventually you get Jupiter. If you kept adding mass to Jupiter, eventually you get an even smaller planet up until some threshold, and then you end up with a star.
Right. There's a good one here. Early on, I wanted to do this one here. Man, there's a lot of great questions. All right, so Arjone asks, what's the most interesting question that you want to see answered about planets or exoplanets? Apart from the life question, obviously, but the actual planets themselves, or even Saturn.
That's a good question. Maybe there aren't any interesting questions left to be had. I think one of the big things that we don't understand yet is how we get such tremendous variety in exoplanets. Astronomy sort of assumes that things happen in sort of neat, orderly ways, and that a star forming in one place is pretty much like a star forming in another place. And given the vast size of space and the fact that the universe is made up of basically the same stuff everywhere, those usually seem to be pretty good assumptions. And like sort of our bedrock assumptions are that physics works the same everywhere. And that's definitely true. But somehow when you get to these sort of more complicated, higher order problems like protoplanetary disks forming planets, we get this tremendous variety that just seems, our understanding of how planets form seems so totally inadequate to explain. Like, set aside the fact that right now we can't even imagine how any planet forms from start to finish. Even when we overcome that challenge in probably the next few years, that just no two exoplanet systems look even sort of like vaguely similar. And that's a challenge when we can't actually do what we do in the solar system, which is go up and study them individually as whole worlds. We have to sort of think of them in aggregate because we're never going to image the surface of these planets or know the atmospheres of most of them. But thinking statistically like that seems so inadequate when their variety is so great.
And so it's like, are we normal? Is the question.
Yeah,
right?
I mean, it's a good bet that we are normal, but it's also a pretty good bet that the distribution is extremely broad, and that there's that 60% of planets fall within this range of normal, and so that there's billions of planets out there that all are basically normal, but are all profoundly different from one another too.
Yeah, and every time that we find new planets, we get to add another data point, and so that's one of the real benefits that Tesla's going to do is it's just going to tell us here's 13,000 more planets to help figure out if the solar system is normal or weird. Because I guess if it's weird, then that does bring back to that life question. Maybe life is rare, but if it's normal, if we are normal, then it comes back to like, why don't we see any other evidence of life? So it's fascinating either way. All right. Brad McGashett asks, what are the difficulties and chances of sending a probe into Saturn or another gas giant? So, I mean, we've already done this, right? Cassini and Galileo have both gone into their respective planets, but they both crashed in. So could there be a mission that could somehow be in the upper cloud tops of either of those planets and explore them?
Yeah, you could imagine, we define the surface of those planets basically as where the pressure is about the same as pressure on Earth, 1 atmospheric pressure. And so you could imagine sort of like if you could have an airship in Earth's atmosphere, you could have an airship in Saturn's atmosphere or in Jupiter's atmosphere. The problem that you face is that those planets are just so much bigger, that their atmospheres are so much bigger that you don't learn a lot of meaningful stuff about what's going on in the inner 99.9% of the planet. Like even like the Galileo probe, which went in much farther than either Galileo or Cassini did, only went in like 20 or 30 kilometers, I think, on a planet that is like 70,000 kilometers
right.
In radius. And so even if you imagine that the middle 50% of that is not really an atmosphere, but is more like a sloshy, dense, weird mix, you're talking about, you've only explored, a few tens of kilometers of 30,000 kilometers. And that would be like, going out into your backyard and digging a hole that's like a foot deep or a meter deep and saying, okay, now we can learn something meaningful about the inside of the Earth.
Right.
It's just, that's proportionately about the amount that we've explored the atmospheres of these planets.
So, I mean, you mentioned that, right? That in the planet begins where the atmospheric density is roughly what we have here on Earth. That's very Earth-centric, obviously.
It is.
But that if you get deeper down, a few dozen kilometers, it turns into this slushy. So, like, what would that, if you get down that far, what would that environment? Because I think a lot of people in their minds, right, they're imagining a gas giant as this big, puffy cloud that you fly your spaceship into and explore the internal structure of it. But it's nothing like what your imagination is expecting.
Yeah, I mean, the truth is that we really don't know. There's not a lot of analogs of substances like this on Earth, and the temperatures and pressures, the physical conditions well inside these planets are so unlike anything that we're familiar with that our basic physics equations, what we call the equations of state, that basically describe the relationship between gases and liquids and solids for every element and molecule, they basically break down. And that we don't really, because we don't have a way to do an experiment to test what actually is true, we're left sort of trying to extrapolate and guess from the way they look in places that we can study. But we know that those equations aren't exactly right because they don't reproduce. They don't. When you model a planet based on those equations, you don't get something that looks exactly like the planets that we see. And so the deep interiors of those planets may sort of just be forever unknowable to us because there's basically no technology that would allow us to physically go in there. And it's hard to imagine a way to simulate those conditions here on Earth in a way that's meaningful enough to conduct real studies with.
Yeah. It's like imagine gas, hydrogen, and helium, but it's compressed to the point that it is as hard as concrete, but it's also really high temperature, and it doesn't work like it doesn't work like a gas anymore. It turns into this superfluid, and maybe ice. It just gets weird.
I think of it kind of like whipped cream or something. like what is whipped cream? If you blop it down on your table. It doesn't just like flow under the floor, but it's not rigid like a solid. And at different temperatures, it changes its properties a little bit. But you push your finger through it. It's what is it? Or like what is cotton candy or something like that? It's these weird substances that we have.
It's an emulsion.
That there's weird things that are sort of like, at least for me, like the best mental pictures of what those things must be like. And you can imagine being immersed in whipped cream. You're not really going to understand a lot about what's going on because it's opaque and blocking your ability to reach out and understand what's happening.
Yeah. And so if you're like, we can promise you that it is not, if you were to fly your spaceship into Jupiter or Saturn, it is not like flying into a cloud. But we can't tell you what it is like. It's like flying into whipped cream, but it's not that. I love that. Yeah.
Space cream.
But it's not. It's, now that you've imagined flying into whipped cream, it's not like that because you can't imagine it. I think it's a great way to look at it. Where'd it go? Oh, Roger Wilco asks, why not send a probe lander to study the active volcanoes of Io? What do you think about that? No one's ever pitched a mission to Io. Why not?
I think one of the reasons is that we can learn a tremendous amount without having to land there. Because the great thing about volcanoes, and this is true on Earth, like it's true on Io, is that they're like spewing out all the evidence in a place that you could easily go and see. And so, Galileo could taste the material basically that inundates basically the whole Jovian system. And that tells us pretty well what's going on the inside. It's not like Europa, where the surface is obscuring the ocean that must be inside. And it's not like Titan, where there's an atmosphere that's obscuring the surface. In Io, we can see the surface, and we can see the stuff on the inside coming out. And you can imagine it would be a pretty harsh environment to have to work in. And so it'd be a challenging place to land, and then you'd kind of be rolling the die that you wouldn't just get like covered up in lava or something like that.
And it's the worst radiation environment in the Jovian system. Like it would be.
Oh yeah, it's right in the Jupiter Taurus. We're having to armor up the Europa Clipper just to make these flybys of Europa, and Io's even closer to Jupiter than that. So we're talking about the kind of thing that is, for example, on Juno. But if you add all that mass, they have literally have metal plates to protect the instruments on Juno, then it's so heavy it'll be really challenging to land. You won't be able to bring enough fuel, and then you'll end up with just such a compromised system on the surface that you probably won't make that many meaningful measurements that you couldn't make from Jupiter orbit.
Without all the mystery of trying to explore, say, Venus, which is under all that thick cloud, and who knows what magic is down there. But with Io, we just get, as you say, we get to see it from space, and it's throwing it all up, which is great. It's good. Have you watched the Netflix movie Io? I haven't watched it. I can't bring myself to do it.
No, I haven't watched Europa Report either. I'm way behind on
Europa Report is pretty good.
Movies.
Yeah. There was one on going to Titan as well. I don't know what it is about. Everyone's like, we got to escape Earth, and we got to go to the worst places in the solar system.
You have no idea why people would want to escape Earth in 2019, Fraser.
and go to Titan or Io. Yeah. Let's see here. Arnstro wants to know, what are the best, most accepted models of planetary formation, and what are the biggest drawbacks?
Well, so we have a pretty good idea of how we form planets out of stuff that is sort of like meter-sized. And we have a pretty good idea of how we form stuff up to about the size of a grapefruit from planetary dust. What's been the challenge for quite a long time is to grow things from the size of a grapefruit to the size of a small boulder. And that's because those very small things are light enough that they're basically blown along by the dust and the gas in what we call coupled to the disk. So basically, as the disk rotates, they move along with it. And it's like water flowing in a stream. Nothing wrong with that. really big things, bigger than your boulder, are basically heavy enough that the force of the disk, the force of that gas hitting them, isn't really disturbing them. You can imagine a big boulder in the stream isn't getting pushed aside. Stuff in the middle is in this weird thing. It's kind of like a leaf or a stick in the stream, where it's too heavy to be brought along with, but not heavy enough to sort of shrug off that influence. And so what ends up happening is it experiences a lot of drag, the same kind of drag that you get from dropping an object in Earth's atmosphere. And that drag steals energy from the object, and it basically spirals into the star and gets eaten by the star in a really short period of time. And we have some ideas around this. Like, one idea is that if you can form a gap in the ring, or a gap in the planetary disk, then objects won't be able to migrate across that gap, and so these sort of grapefruit-sized objects will pile up on the outer edges of these gaps, where they can then clump together into larger structures that eventually can survive. Another idea is this thing called pebble accretion, which has been sort of in vogue in the last few years. And the idea here is that once you get to sort of pebble sized, so before you grow to the grapefruit that is getting sucked in, they have enough gravity sort of between pebbles that larger boulder-sized objects just kind of spontaneously collapse out of areas where these pebbles are. And it lets you basically jump from things that are still mostly connected to the disk to things that can act independently of the disk without having to spend a lot of time in that messy in-between time where you end up just getting sucked away and die.
Mitchell Peterson has a very serious question. If the moon is technically in the Earth's atmosphere, why doesn't everything smell like cheese?
Oh, maybe what we think of as air is actually the smell of cheese.
Yeah.
And we just don't know it because we've evolved to think of cheese air as our natural habitat.
Where was the good one here? Okay, so Paul McDonough asks, what do you think is the most unusual to us planet that is possible to exist? Like, can there be a diamond planet or a gold planet or something even crazier, like an antimatter planet? Weirdest possible planet.
Probably not an antimatter planet. I think composition-wise, I mean, you can imagine the universe is a big place, and all sorts of things could cause you get those weird planets like that. But I actually think that the weirdest planets are not going to be sort of compositional, because the universe, the galaxy, really is pretty uniform in terms of composition. And in fact, if we saw a planet that seemed like it was made of like one material, I think that would probably be a pretty good sign of a place we should look at closer for evidence of sort of intelligent life. Because just like the odds of that happening, like if you take a bucket and you put in like 100 green M&Ms and 100 red M&Ms, and you like shake the bucket up and you dump out half the M&Ms, the odds of getting 100 green M&Ms to fall out would take like the lifetime of the universe to happen. Even with these tiny numbers, the odds of getting that kind of separation is just infinitesimal. And so the odds that you get an entire world that is wholly constructed of some complicated element is just astronomical in the popular sense of the term. Now, we do see objects like, for example, the asteroid Psyche that seem to be made of mostly one substance. And we can think of physical explanations for why that happened. In Psyche's case, it was the core of a planet that differentiated, and all that metal sunk to the center, concentrating it, and then the planet broke apart. But if we saw like a Jupiter-sized object that was seemingly made of a single thing, I would be pretty suspicious of that. So I think the weirdest planets are going to be ones that are weird for other reasons, like weird for what we'd call dynamical reasons, like how they're orbiting about their stars. You can imagine all sorts of weird combinations. We already know of planets around 3 or 4 or 5 stars, but you can imagine those kinds of complicating situations getting almost like arbitrarily complicated. And they might not last forever because those kinds of configurations tend to be unstable. And eventually, some of the objects will either get swallowed up by others or kicked out of the system. But for short periods of time, you could imagine a scenario in which you have planets like figurating around a bunch of different stars in a way that would then lead to a lot of weird things happening on the surface.
Yeah, I mean, they found a planet that has a year that's 13 hours. I think, is that right? Like just like a really tight orbit around its star. You can imagine situations when you think about even our own solar system, right? The fact that we have the rings right now around Saturn turns out is actually they haven't been around for very long, and they won't be around for too much longer, solar systemly speaking. Same thing with Phobos at Mars, which is going to crash into Mars at some point. So it's these dynamic situations that we get this glimpse of this situation that isn't going to last.
Yeah, you can imagine almost anything happening for a short period of time, but compositionally, those kind of things tend to stick around. And you'll see people write press releases now and then saying, we found this planet where it's, a diamond atmosphere or something. But probably that's not a whole planet like that. We just can't see past the atmosphere to see what else is going on down there.
1964 Sleepy asks, how dangerous are the Van Allen belts to our astronauts? I mean, if we're going back to the moon. Have you done any episodes on the Van Allen belts?
I haven't. I mean, we don't spend a lot of time in the Van Allen belt, and that's key. You go up and you sort of puncture through them in a relatively short period of time. And we've had so few astronauts spend time beyond the protections of Earth's magnetic field that we don't really understand what those risks are. I remember a study like a few years ago that suggested that the Apollo astronauts who actually went to the moon, whether they orbited or walked on the moon, were suffering from like heart disease at like a 5 times the incidence rate of people in their age cohort, even though that these were selected as like the healthiest, fittest humans out there. And now when you only have a couple dozen astronauts who made that trip, then you're stuck in this world of small number statistics where you really can't to know anything. But this is a thing we're just going to have to take a leap of faith on. There's basically no way, because it's unethical to just like irradiate people here on Earth. And so we're going to have to settle for people volunteering to irradiate themselves on these early trips. And then it'll be 50 years before we know what the real damage that, a year of space travel to get to Mars actually would take, or a year of working on the surface of the moon would actually incur.
And I mean, the Van Allen belts are the least of your concerns when you fly out beyond the Van Allen belts. That in terms of radiation, they're sort of the easiest to protect from. And as you said, you go fast and you only experience a tiny amount of radiation. I think during the Apollo missions, they experienced about 1% of the radiation load that NASA was prepared for. So that was not a problem. If you want to go to Mars, it's the daily pummeling by galactic cosmic radiation that you experience. I mean, the Curiosity rover had a radiation experiment on board, and it was well and truly radiated by the time it got to Mars. That anyone willing to go to and from Mars via space is going to need to accept a fairly significant increased risk of cancer at some point in their lifetime, and possibly a deadly solar storm that could sweep past if the timing is bad. So it's serious business out there.
Yeah, we have a lot we haven't figured out.
Yeah. Arjun asks, do shepherd moons actually extend the life of planetary rings?
I don't know exactly how to interpret that question, but I think I would say yes. Rings in general tend to diffuse away over time, and you can imagine why this would be. If you had a narrow band of stuff that was all orbiting with like slightly different directions. They're going to be bumping into one another. And those bumps sometimes will knock them towards the core of that area, but then they'll hit something else pretty quickly, and so they're not going to like go through the core of that ring. But other times they will knock them out away, in which they don't have other things to run into, and so they can travel along farther paths. And so they kind of random walk their way farther and farther away, and eventually some of those particles will get pulled into the planet on the inside and drift away on the outside until maybe they get blown out by the pressure of light from the sun. And shepherd moons basically act gravitationally to redirect those particles back towards the core in a way that can really confine the rings to be very narrow. And the best place we see this in the solar system is at Uranus, which has these incredibly fine scale rings. Now, our confusion at Uranus is that we don't see shepherd moons for each set of rings. We see them for a couple, but we don't see them for all of them. And so either there are smaller moons than we've seen, although people have reanalyzed the Voyager data and suggest that those moons can't be more than a couple of kilometers across, at which point they might not have enough mass to really effectively be shepherds, or there's another process that helps confine rings. And some people have suggested that some of those rings are a little bit elliptical, and that elliptical nature of the different rings sort of out of phase of one another can serve to sort of play the role of shepherd moons for each other in a way that allows them to stay confined even if the moons themselves aren't there. But until we go back with the Uranus orbiter, we won't know that for sure. This will be one of the things that I think will be solved pretty easily once we go there and have high resolution and long time period studies of the rings, because Voyager returned excellent data that really gives us a good sense of what's there, but we don't know how it's changing over time. And sort of the subject of my thesis was to claim that Voyager was sort of wrong to conclude that the rings are generally static. And what Cassini has told us is that the rings are highly variable on the period of hours and days and months and years and even decades. Yeah. And until we have something there at Uranus to observe for years, we won't really be able to disentangle what's happening.
Well, we're right near the end of our hour. It just goes by in just a heartbeat. By. Yeah, exactly. But so people want to follow what you're doing right now. Obviously, of course, join us every week on the Weekly Space Hangout. You're one of the co-hosts. But where are some of the other places that people can see some of the projects that you're working on?
Yeah, honestly, the Weekly Space Hangout is about the best. I have gotten very lax in my use of social media. You can follow me at Morgan Rehnberg, REHNBERG, on Twitter, but I post very infrequently these days. I have been making an effort to be a little better about updating my website, morganrehnberg.com. I recently threw up some info about some of the projects that I've been working on at the museum, as well as links to some of my recent episodes of SciShow. But I haven't done a particularly good job lately of sort of disseminating all that's happening.
I know the feeling. It's like at a certain point, I'm sort of just generating so much content that I don't have time to tell people where and how I'm generating all of the content. And it's like, I think at a certain point you just flip and you no longer just have the energy to tell people the things you just did.
Yeah, I used to tweet religiously about everything I did.
Yeah.
No more.
Yeah.
Of course, if you live in the Dallas-Fort Worth Metroplex, as millions and millions and millions of people do, you should swing by the Fort Worth Museum of Science and History and say hi. If you see me wandering the halls or at one of our evening events, come up and say hi. I always love to meet.
Has that happened? Has someone come and recognize?
It happens, every couple months, somebody will yell, "Are you Morgan?" Across the way, and we'll sit and chat for a few minutes, and it's always a good time. So come say hi, watch the Weekly Space Hangout, and check out my website.
And Morgan, I just want to say for me and for I'm sure all of the fans of the shows that we do, that it's been an absolute pleasure working with you and and having you bring such a deep level of knowledge and enthusiasm for everything you do. You absolutely make the show so great, and I always look forward to, when you steal the cool story, I'm okay with it because I know that you're going to do a great job. And I just thank you, man. Thank you so much for all
I'm
of
just
these
glad
years
there are
of
other people out there who get excited about the world and are willing to share that with me, because otherwise my poor girlfriend would be inundated and I would be a bachelor once
Right.
again. So really, you're saving my relationship.
Oh, there we
by
go.
Watching the Weekly Space Hangout and watching our videos and
Right.
reading my stuff. So thank you, world, for keeping me alive.
Well then you're welcome. All right. Well, we've reached the end of the hour. We're going to try and be prompt both in the exit as well. So before we go, I want to say a big thank you to everyone who is watching. Thanks to everyone who threw the questions at us. It was awesome. There was great questions there. And thanks to the moderators, although it seemed like everyone was really well behaved today. It was great. And Morgan, thank you so much. And we'll see you in 2 days on the Weekly Space Hangout.
Thanks for having me.
All right. Thanks, everyone.